was not in my plan to do this, but yeah, this is November 23 and well, yeah. This is the, this is in the CKVM, we are applying recursion. This is, so we mainly what we are doing is we're working with the Starks. Starks, the cool thing with Starks is that the recursion is very natural. You don't need to work with cyclic cycle curves, different curves in cycling. And, you just work with a single prime field and you just do recursion. The only thing you need to do is you need to use the hash function that actually is in the same prime. But here, for example, Poseidon or any arithmetic function works well for this. Okay, but Starks are very good for recursion. It comes out of the box. Okay, that's the first thing. So you can do with the Starks, but it's, I would say, at least it's more difficult. Then is you end up doing foldings instead of pure recursions. But the idea is the same. But with the Starks is much easier. Okay. So this is, we have the basic proof is what we call a batch proof. This mainly is, so a batch can contain many blocks, and this is about, more or less about 10 million gas Ethereum blocks, more or less, okay? Depending on what you are doing there.
And does that directly impact the tangent generated proof? Is it dominated by gas utilization? Or?
This batch is constant, it's monolithic proof and it's constant time. Okay. The only thing is that you cannot do everything. If you're doing a group of ketchups, you are going to be out of counters.
Okay, I see.
You can prove that you are out of counters. So, I would say normal user will not affect unless you are doing some crazy stuff.
Yeah.
Okay?
Is there a scheduler or something like that behind that actually creates these batches?
What though?
Is there any scheduler or something behind that actually creates these batches?
Well, yeah, there is actually there is a sequencer. The sequencer is generating blocks, okay, and if you want, they already pack them in batches. Okay, they see that they fit, and okay, this is going to be a batch. This is going to be another batch. This is going to be another batch, and then of course you need to generate the proofs. The cool thing is that the proof you can generate them in parallel. You can have like 10 servers, one generating the proof for batch 1, then for batch 2, then for batch 3, and you pipeline them. Okay, so proofs is not. So the proving is not a bottleneck for a ZK rollup. Okay, that's my mantra. It's, of course, it has a cost. So if you have a very crowded, very loaded chain, you will need to generate more proofs. So you will need to put more servers in parallel. But there is no limit. You can scale. You just put servers and that's it. Okay.
What happens in a flow, say a batch fails?
What then?
What happens in a flow if batch fails in growing?
No, batch are designed for never fail. Okay? And and this is important because this is, for example, when we have forced transactions, so a user can put any transaction that they want there, and then maybe they put a loop of ketchups there, okay? And the trick that we are using here is that we, internally in the proof, we have the counters. So before doing a ketchup, I'm just counting how many ketchups I already did. If I don't have enough ketchups, I just don't execute the ketchup. I'm just saying, okay, I don't have enough ketchups. The proof is valid. Maybe the transaction is going to be a no operation transaction. Okay, but the proof is valid. And the important thing is, no matter, so you can have a data, and it can be a random data. You always will be able to generate a proof. Okay, so we guarantee that we are going to generate a proof. In the smart contract, we do some checks. For example, we limit the quantity of data that you can put in a proof. Okay, so that you will be able to hash it inside. Okay, so we guarantee that by smart contract. But if a smart contract accepts a sequence, then you will be able to prove that by definition. Maybe there is a bug, but if there is no bugs, this is how the system should work. Okay.
But does the sequence attest to the new state, or you're just saying just the sequence turns out?
No, the sequencer does not prove anything. I mean, it just computes. It's like a normal client. They just create blocks. Here, I mean, and it is more an internal thing. It's we are checking. So when we are sequencing before giving a block for correct, we do a kind of a double check, and we check that it's going to be provable at sequence, because we want to detect that at the beginning, and this works. I mean, this guarantees that we are not going to stop the network. Okay, but it's more a protection than a need.
I guess what I was wondering if your
They
question
already
is
has the
like,
hash order,
So that the design is, so the specification is that you will be always able to generate a batch, always. So you can put random data, you can put malicious data, you can put whatever transaction. So whatever thing you do, the code with this at the end is a kind of a processor and a code that's with it. It needs to take all the edge cases of that. I mean, invalid RLP or non-canonical RLP. I mean, here there is a lot of logic you need to take into account, but that's part of the specification. I mean, you need to think of all the possible cases here.
Yeah, the batching here already guarantees the partial order.
Yeah. Okay. So here going to recursion. So here we have different batches. This is a monolith. This is just a proof. Okay. I mean, it's a big proof. I mean, it's a proof that it takes a couple of minutes in a 128 cores machine with half terabyte of memory. Okay, so it's a huge machine, the biggest machine that you can, let's say, buy in the market. Okay, but it's a huge machine, a huge standard machine, let's say it that way, and it's a machine that in spot instances it costs about between $1 to $2 per hour. Okay, and it takes less than 2 minutes to generate one of these batch proof, just 2 minutes. And depending on these contours, but more or less it can do about 500 Ethereum transfers, about I think it was something like 80 or 90 token transfers, or 30 or 40 swaps, more or less. And that's something between 5 and 10 million gas. Okay, depending on the kind of transactions. Okay, so we have many batches. First, we have this step is very much a kind of a compression. So here is a huge proof. Okay, so the idea here is that in the Stark we generate the first proof that we generate is a huge proof. So it's a proof that verifying that proof is relatively costly, but it's already a proof, but it's big. So here what we do is a set of steps. I mean, it's just we verify a proof with another proof until the size of the proof is more or less the same. That means that you need to do a couple of steps. Okay, but that's just for compressing. It's a compression steps. Why? Because the recursion part, I want to work with a relatively small proof, a proof that's easy to generate. Okay, and here, okay, so this is very much the. So then we have a recursive part. A recursive part, I mean, here we have a recursive tool. This is a proof that actually includes two proofs. So it includes two verifiers. So it's a proof that includes two verifiers. Okay? So it's a proof that verifies two verifiers. And it's joining one proof in another proof. And then you can do this as many times as you want. We will see now how we do it. Okay? And of course, in the last step, we convert this Stark to a snark to send it to the blockchain. Just because verifying a Stark on chain is very expensive. So you can do it. So we just have a normal snark that Actually, we are using flong to verify the last, the final step. Okay, so and then this costs like 200k, around 200k gas in the blockchain. But it's a proof that proof as many batches as you want. Okay.
If the proof fails, if the aggregated proof fails, can you exactly point out which of the exact block failed, or you have to like you have to guess which failed? Like if the aggregated proof fails, like all the proof fails.
No, cannot fail.
I mean, it fails to verify.
What means fails?
If the verifier does not let it go.
That means that the proof was not correct.
Yes.
So no, all the proofs. I mean, no, all the proof. They cannot fail by design. So the first one is the less obvious thing, okay? Because this is controlled by the user, but this is verifying. So if this is valid, here what you are doing here is verifying the proof. If this is valid and this is valid, then you are able to prove that those things are valid. Cannot fail if the two proofs that you are verifying are valid. Maybe you are doing something wrong. Okay, but it cannot fail. Okay, so if it fails, is that there is a bug in the system. Okay.
Act of God, maybe. Act of God, flip a bit.
I mean, if I tell you that never a proof fail, I would lie to you. But that's when the proof fails is because there is something wrong that we need to fix. Okay. Yeah. Okay. Let's see how we do this. Let's see how we create a proof that generates two proofs. Okay. So here is. Actually, we have a circuit. Imagine that this is imagine that this is. So just take this one. So this is Imagine that you have a proof that. Let me just see if there is better image here. Yeah, this is the basic circuit. Okay, the basic circuit that aggregates two proofs. Let's first try to aggregate two batch proofs, so two basic proofs. Okay, so actually, if you see, imagine that this is a circle. Imagine that this is a circle circuit. Okay, a circle circuit has like two templates. Okay, one template that verifies a proof of a batch, another that verifies a proof of a batch. Okay, here of course the input state. So inside the circuit is connected. So the input state is connected to the beginning of the state. The output state of the first part is connected directly to the input state of the previous one, and then you go to and then this is the output state. Okay. So this would be, and this is this is the basic recursive circuit. We call this in serial because it goes one after the other. Okay, so you prove one batch and then you have this serial one. Okay. This would be in parallel.
I've always wondered why the number of inputs to like a node in the recursive circuit tree, right, is 2 instead of like more than 2. There are design decisions for like it always being.
Well, you can have, so I mean, in the case of the SGBM, we have many inputs, but the main input is you have an old state and a new state. Okay, so you have an old state, you have a set of transactions that you want that in general are private inputs, and then new state. Of course, we have some way, so we have other inputs just to validate that the transactions that we're processing are the ones that are committed in the state. Okay, but the basic public inputs of the circuit is the old state and the new state. Okay, yeah. So this is the input state and the output state. Okay. Yeah. So first thing that we do is, okay, so we have a proof that verifies a batch, a proof of a batch, okay? So here, imagine that we have a template in Circum that actually verifies a batch proof. Okay? So we just create another circuit with this template that verifies the batch proof. Here, the circuit, of course, the basic proof that generated is part of it's like a private input. So we have a private input. And here the only thing, of course, this state has an input state and the output state. And here we just add, we call it root C. This would be, at this point, with this circuit is useless. It's just a public input that we just add here. But in this case, here is like a fake, it's an input, but it's an input that's, we can put any value here. Okay, so it's just an input that's inside. Oh, well, I need, well, I don't know, I need like 10 minutes. I don't know, if you want, I can stop.
It's Daniel's session after that.
I gave up my session. Everyone's gonna learn more from this.
It's just 10 minutes if you want, I mean, I don't care, I already know that, but.
Yeah.
So, okay, so with this I generate the proof, and here, so I built another, well, this is a built another, so this is the same thing, yeah? So it's the circuit, we have root C, that, well, here I do the same, so here is this is the adapter circuit, okay? So to verify, so I do this again, another time, okay? So I generate another circum circuit. In this case, here I have the verifier is not the general verifier, it's the adapter circuit. Of course, the root C needs to be embedded directly here. Again, this is in the adapter circuit, this is useless, okay? Input a state, and okay, so I have this, okay? Okay? But, so here we are not going to use this circuit, but it's important that we have this adapter. This is a template, it's a circuit template that actually verifies this adapter circuit, this actually verifies the previous circuit, okay? So, we have this circuit, and this template, this is in yellow, this is what we are going to use, okay? So this is a template that actually verifies the previous circuit, okay? And now, what I'm doing is very much this, okay? So I'm just taking this template that verifies the adapter circuit, and I create a circuit where actually I have two verifiers inside the circuit, okay? And, well, the root C, I connect them to both sides, okay? The input state, I connect it in serial, and as a public input, I have a P1 and P2 adapter, okay? So this circuit actually would verify two basic batches. Okay, actually, it's batch needs to be, you need to, with the proof of the batch, you need to generate the proof of the adapter. Okay, but it's a single proof, and then you can verify this adapter with these two ones. Okay, this is, if you want. This is the recursive one, is the adaptive circuit. Okay, so and the only thing that does this adaptive circuit is add a public input. The only thing that it does, it just adds this special public input. Okay. Okay. Here, the next thing that I do is, okay, yeah, important here, one thing that's important. This circuit, so this circuit for the verifier here, we have the verification key. So the verification key is an input. So I abstract the verification key and I put it, but in this case it's hard-coded. Okay, so here there is an input. in this case of the circuit, will be hard-coded to the verification key of the basic verifier circuit. Okay? Okay? Here, of course, I'm not using this, but here I would adapt here. When I'm using here, I would adapt the verification key. Okay? But what I can do here is, okay, I have another public input that I'm saying if it's a basic proof, so a batch proof, or is another aggregated proof. If it's a batch proof, I hard code with the adaptative proof. So in order to have the same that I had here, with a hard coded adaptive here. But if I'm setting here a 1, if I'm setting here a 1 and saying, no, this is an adaptative, this would be an adaptative circuit, then I'm just selecting the one that comes from root C. From this special input that I put here. Okay? And, okay, I have this circuit. Okay? I have this circuit, but just selecting here, I'm just have a multiplexer that either selects the root C or the hard-coded one. And I can put a 0 or a 1. Okay? Now, I'm generating, again, another circuit where here I'm just putting a verifier of this circuit. Okay, so here is I have a template. Okay, here is going to have. This is going to have a. It's going to have a. Here is going to have a verification key that's going to be different because that circuit is different. Okay. I just hard code this verification key, and I have this template. Okay, so this is a circuit template. Of course, this is green because it's a different circuit. It's a different verification circuit. Okay. But the cool thing is that they have exactly the same. So this template has exactly the same public input, so the same inputs and outputs. And I can make it to have the same structure. Actually, I can make it to be exactly the same. I mean, if you see the circuit code of the green circuit and the green circuit and the yellow circuit, it's exactly the same. The only difference is the verification key, which is a number, and I'm just extracting. I mean, I'm just taking out this verification key and putting it as an input. Okay, so here. So actually this circuit is green or blue. I mean this circuit is, so this template is exactly the same. Okay, so let's put it here because it's exactly the same. So here if I'm putting a 0 or a 1, so if I'm putting a 0, the verification key is going to be the verification key of the basic circuit. If it's a 1, it's going to be the verification key that I'm putting here. But here I have a chicken and egg problem. Okay? So that's why I take it from this root C. So that's why I'm taking this special input here. So here I could hard code. So here I could hard code for the green one. But I mean, the green one is the verification key of this circuit. So I cannot generate the verification key of the circuit that is myself. So what I'm doing is, okay, I'm just taking the one. So this circuit verifies the thing. As far as a public input, I'm setting as public input, I'm setting in root C, there is the verification key of the same circuit. Okay, this is the main trick. So it's the verification key of itself is passed as a public input of the circuit. And I need this adaptative circuit in order to have exactly the same inputs so that the verification key is exactly, the verification template is exactly the same. Okay? So that means that, okay, the circuit of course can be, if root C is the, so the circuit is verifies itself or either itself or either, so either an aggregated proof or either a basic proof, and two aggregated proof can be aggregated and you can put. As far as this root C is the verification key of this circuit. Okay? So at the end, at the final, so I can have another circuit, which I am just taking exactly the same key. But here already, this is the final circuit. So here already I hard code hard code the verification key with the verification key of the aggregated circuit of the two circuits. I put it here, and then here I have a circuit that has exactly. So here, as an input, I can put either a type 1, so a batch proof or an aggregated proof, okay, 0 or 1, and it has exactly the same structure that I had in the beginning. Okay, but this can include a segment, it can include just one proof, if this is a 0, or it can be an aggregated proof. Okay, this is a 1. Here I can put an aggregated proof. The verification key here already is going to be the aggregated proof. So this verifier verifies something that's already correct in there. Okay. So we go back. The main trick is here. So the verification key of the same circuit needs to be passed as a public input, because I don't know now. I will know later on. And then I have a circuit that takes this public input and verifies, depending if it's the first circuit or the aggregated circuit. Yeah. Of course, this allows me to do aggregations in serial, like this. It allows me to do same technique, but aggregations in parallel. Okay. Parallel means you do some sort of aggregation, and yeah. Well.
Should work for trees as well, right?
Yeah, you can work with trees a parallel way, so you can aggregate. But the cool thing is that you don't even need a structure. So you can have a balanced tree or an unbalanced tree. So when we are aggregating, and maybe it's a question before, we are aggregating as they come. So I have 2 proofs, then I just launch a worker to aggregate these 2 proofs. That comes another proof. Well, if I have 2 proofs to aggregate, I just send a worker, okay? And I'm just trying to aggregate as much as I can, but as they can. First come, first serve, and depending on the workers that I have, depending on the provers, well, I'm going to try them to be working as much time as they can. And they are doing the best work that they can do at each moment. So I'm aggregating. Once every half an hour, I just get, it was not, so I'm going to here, I finish to aggregate whatever is finished to aggregate, and I send it to Evo.
Workers, do you mean a machine or a...
We have the idea is we call the aggregator. The aggregator is a single machine that some host coordinates, and it's kind of a mining tool. So we have an aggregator that's just giving, right now, this is going to be different. But right now it's just kind of a mining tool. I mean, there is one aggregator, it's a simple machine, a very small machine, that the only thing that says is, and here many validators, many provers can connect to there. And depending on the provers that connect, you just give, okay, you do this, you do this, you do this. And when they receive the